Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. M. Lois Tiffany Endowment, and by gifts from friends of the program.
So I want to begin by thanking the Michigan Department of Physics for making this possible, and also the Michigan Society of Fellows for allowing me to speak today. So what you're going to see today is a non-fictional account of a film by Stanley Kubrick called Dr. Strangelove. And I have to tell you ahead of time, I have to say this, any bad jokes or humor in here is really a reflection of a theoretical cosmologist, not the Department of Physics at the University of Michigan. So I'm going to start with a very, very basic question that all of us could ask as children, and that is, why is the night sky dark? Because after all, at the beginning of in the 1900s, if you looked out at the sky, we knew it was infinitely old, the stars had been there for an infinite amount of time, and the universe was static and not expanding. And so therefore, as time went by, all the light from stars should have ended on the Earth, and we should see it, and the night sky would look something like this, and you would never have darkness. And so at the time, this was a profound problem. But today, we sort of laugh at this, and the answer is obviously that the universe is expanding. So this was first found by Hubble in 1929 when he was looking at galaxies that far away and looking at how fast they were moving away from us. He deduced that they were moving away from us at a rate that was proportional to how far they are from us. And since this time, we've refined this in fact, if you took a physics lab, you might fail if you turn this report in. But since that time, we've refined this to at least 5% error. We know exactly the rate the universe is expanding at. But so what will be important for us today is just the fact that the universe is expanding, and as the universe expands, it cools. And this very simple idea leads to profound consequences. So if we take what we know about particle physics and we put it in this background of our universe that's expanding and cooling, if we start with we start out in the very hot universe. We have quarks, the particles that make up protons and neutrons. As the universe cools, it becomes cool enough that these can join together and form, for example, neutrons and protons. As it continues to cool, then these elementary particles combine to form atoms. And then those atoms form to combine molecules, and so on and so forth, until we form galaxies and the largest structures that we see today. And then we're in the universe where we are today. And this is all the process of just combining what we understand about particle physics and what we understand about the expansion of the universe. So this is a long story. It's very impressive that given this huge history of the universe, we very, very well understand, and in agreement with cosmological observation, the majority of the history of the universe. It's only sort of the first 3 minutes that are perhaps a little bit of a puzzle. And so that's what I want to talk to you about today. And in particular, I want to focus on this period of time here, which is when the temperature of matter cooled to the point where photons could no longer, or light could no longer interact with matter. And so this is a very important observation, because when light can no longer interact with matter, this is giving us a photograph of the universe at this time and the way that the matter and energy looked at that point in the universe. And so by looking at this picture, we're looking back at exactly this time, the way the universe looked, which was around 380,000 years after the Big Bang, whereas today we're at about 13.7 billion years. So this is a very, very early picture of the universe. And so this is the picture that we first took. So this is very uninteresting. But it's actually much more interesting than it first seems, especially if you're a cosmologist, because what this tells us is that at 380,000 years, the universe was extremely smooth, and this picture represents the temperature at that time, and you see there's no variations in this temperature at all. And so from this photo, we know that the universe was very, very smooth in its earliest moments, and this is accurate to 1 part in 100,000. So that means that if there were any differences in temperature, it was 1 part in 100,000. And so today, at the time that these photons escaped matter, the temperature was around 5,000 degrees Fahrenheit, so it was the very early universe. Today, this represents sort of the vacuum that we live in, this, out in space, and it's at a temperature of minus 454 Fahrenheit. So that's the way this picture looks today. So now what I want to do is I want to tell you a little bit more about how we get this, this picture. And also, you might wonder why, if this is a picture of the universe that's supposed to be a three-dimensional spatial dimensions that I look out in, why am I putting this on a two-dimensional surface as an oval? So this is a film from NASA's website. I can't take credit for this. We're going to zoom in to our location and try to give you an idea of where such a map comes from. So this is our galaxy. We're moving into our position. So here we are. So now we want to look out from the Earth around us in 3 dimensions. And then we're going to take this three-dimensional thing and project it onto the surface so we get this graph that I was showing you. And so we can look at the universe in all different visible wavelength and different wavelengths of light. And what we're interested in here is the microwave wavelength. Of course, current experiments are looking at all possible wavelengths. But the one we want to focus on today is the microwave. And you saw as this, as we increase the contrast, we look more precisely at the temperature differences. We eventually, when we turn it up to 1 part in 100,000, we see there are in fact small differences in the temperature in this observation. So this has been a great accomplishment. So this was one of the first measurements of this cosmic microwave background. And we see that the difference between the green spots and the blue spots is 1 part in 100,000. So as the years have gone on, we've been able to measure this more and more precisely. And this animation shows you how our view of this background has evolved in time. And so for just a curious fact, for those of you who know who Stephen Hawking is, Stephen's claimed that these are his initials that you can see right here. But so using this picture that tells us that there were very, very small differences in the structure of matter and energy, which was taken by these free-streaming light afterwards, we know that there were very, very small overdense regions in the early universe. Very, very small, 1 part in 100,000. But because gravity is always attractive, as we let these small fluctuations evolve in time, that's actually what led to the galaxies that we see today. So here's allowing the universe to expand. Because gravity is always attractive, these regions that were underdense became more underdense, and the overdense became more overdense. And the matter collects in these valleys and forms the galactic structure we see today. So it all came from this very small fluctuations, these very small temperature and energy and mass differences in the early universe. So we've actually had a couple Saturday morning physics lectures on this. I don't want to say much more about it. It's an amazing observation. But what we want to try to do today is we want to ask the question, first of all, how did the universe get so uniform? How did it have this 1 in 100,000? It was smooth to that point, and that's already difficult to explain. And then the next question is, we do see that there's some very, very small, if you like, primordial seeds that seeded this, first the photograph we saw of the cosmic microwave background, and later other observations, and eventually the way the galaxies line up. It's all coming from these small fluctuations, and at the time, well, I'm actually historically telling the story a little bit in reverse, but there was no explanation for where these small contrasts came from. So let me give you an idea of why it's difficult to explain why the universe is smooth. So if our universe, the entire universe, is represented by this gray sphere, then we can't see the entire universe. We never could, we never can. We can only see what's had time to travel to us, the light that's had time to travel to us. So that's our light cone. And so this red circle represents the visible universe, which is what most of us mean in everyday speak when we say the universe. It's what we can actually see of the universe. So in standard cosmology that's filled with ordinary radiation or matter, as time goes by, the actual universe expands, and the part that we can see of the universe is expanding at a slightly faster rate. So we see more and more of the universe every day that goes by. And so the problem with the smoothness that I was discussing is that in the past, the amount that we can see is also the amount that can talk to each other. And if the things can't talk to each other, why would they be at the same temperature? And so when we're seeing more and more of a universe that never talked to itself, how do we understand the fact that there's very, very small differences between the temperature outside this region and inside? And this is called the horizon problem. It's also related to several other problems that people were trying to solve at this time. And so the solution is something called inflation. So this is actually good inflation. So this is the cosmological notion of inflation, which just means that the universe went through an exponential or very rapid and very large increase or acceleration sometime in its past history. So in the inflation picture, this is what we have. We again start with our visible universe in the red. But during inflation, and I cannot, of course, fit what inflation really does on this slide, but the actual universe increased very rapidly by a very large amount, and it happened so rapidly that the amount we could see did not change at all. So the amount that we could see stayed fixed, but the actual background of the universe expanded much, much faster than what we can see. And so today, when the expansion proceeds in a normal universe, like we're filled with radiation and matter, as the expansion continues today, what we're seeing is actually something that was in contact in the past. And this is the idea of inflation or accelerated expansion. So at this point, I'm presenting this as just an idea. So you can ask, how much did the universe expand by? And what we know from observations is that it was at least a factor of 10 septillion. And if you don't know what 10 septillion is, that's this big number. And this all happened in at least 10 to the minus 34 seconds or less. So this is an incredible property that happened very, very early in the universe. So you can ask what causes inflation, and many people have ideas for what the answer is. But to actually address this question for cosmological inflation, I'm going to need to introduce another sort of mysterious question that was, in some sense, not related at all. And that is the idea of where does the mass of particles come from? What is the origin of the masses of our particles? So in the modern view of how we understand this question, the masses of particles arise from the interactions with the vacuum. All right, so everyone looks blank-faced, as you should. I know I was when I heard this. So I want to relate this problem to something that you're a little more familiar with. So if I go to a cocktail party and I'm filled with a room of sort of colleagues, so it's very boring. No offense again, but so you're moving around this room, and this is the standard cocktail party. But then if a famous person walks in the room, you have a large number of people that will immediately cling to this person, and they will not be able to walk through the room as well as they normally would. So in this analogy, the idea is that a particle is the person that's famous that walks in the room, and the room itself is the vacuum. So this, in some sense, gives a mass or gives a difficulty for the person to move through the room, and this is the concept of inertia. So in this sense, the vacuum is not empty at all because it has an effect on the particle that's trying to move through it. So I want to pause for a moment. This idea of the vacuum and how particles get mass, of course, is going to be tested soon. And perhaps some of you have heard about the experiment LHC, the Large Hadron Collider at CERN, which turned on, turned off, and will turn back on again soon. Professor Pierce next week will discuss this in more detail. But this is a very important experiment for what I will talk about today because it will test our notions, our theoretical notions of what the vacuum is. And actually, so basically you get funding for experiments when your ideas are very well motivated. And basically we know that's the right answer. So it makes us look good. So you run this experiment, you say, see, I told you so. So this is a real important test for understanding of the vacuum. And then given this notion of the vacuum, everything else today I'm saying will follow. So let's go back to this concept that the vacuum is not empty. We know that there has to be something in the vacuum. There has to be some energy, something about it, some energy that's present. And when we turn to general relativity, our theory of gravity that tells us how the universe evolves, this energy will tell space-time how to curve. And then space-time will tell this energy how to evolve. So these are both dynamic. The vacuum is changing. It's an entity. It changes in time. And space-time itself changes in the presence of this vacuum. And so this is a deep connection between general relativity and particle physics. So the first people to note that inflation comes from the vacuum were Alan Guth, who's presently at MIT, and Andrei Linde, at the time was in Russia, but since then is moved to Stanford. And they discovered that the effective vacuum energy on the universe is to cause it to accelerate. So this provides this idea we had. Again, another advertisement. Professor Guth will give this year's Ford lecture, and that should be very exciting, which is on March 25th. And sticking with the theme of my talk, I should point out that Linde defected from the Soviet Union and now lives in California. Okay, so vacuum energy will drive this expansion, this cosmic acceleration period. And so if we go back to our plot of our graph of how the universe is expanding and cooling, inflation corresponds to this very early time. And you can see that we had the Big Bang, that's a question mark. And then once we had the universe, it's very natural in the presence of this vacuum to increase, to do this acceleration, increase by a gigantic amount right here. And this, again, this is not 10 septillion, but this is the best we can do. And then as the universe continued to expand and cool, we have the usual picture that's very well tested by experiment. So now I want to give you a bit of the way physicists look at this. So this is supposed to be a graph representing how we understand this transition, this decay of the vacuum, or how this vacuum evolves in time. Remember I said it's dynamic. So on this axis we have the vacuum energy, and then in this axis we have time. So if we start with some amount of this vacuum energy, inflation will proceed, the universe will accelerate as long as this vacuum energy is present. But as the vacuum evolves, the amount of vacuum energy will decrease until eventually it gets to a level where acceleration will stop. This vacuum will heat up and it will produce the particles that we know about today. And that gives rise to the standard cosmology that we know and love. And the key point for explaining these small fluctuations, or these initial very small overdense and underdense regions, comes from the fact that this process, the vacuum, is quantum mechanical in nature. So what that means is if I think of a lump of this vacuum energy, some of it will reach the end of acceleration at different times in different places. So what this means is that a part of the vacuum in one region can end inflation before in another region. And it's this difference, these quantum fluctuations that lead to this difference that cause these fluctuations we see on the sky today. And so this is quantum mechanics explaining something that's gravitational scale physics. So if this all seems a little mysterious at this point, you actually have real life experience on this. This is an example of a phase transition. And in phase transitions, for example, if I have water and I freeze it, I get patterns in the water, in the ice, because this phase transition takes place in different ways in different places. And these differences are the differences of the phase transition. So I get very different patterns, and these patterns are reflected because water will freeze slightly faster in one region than another, leading to the cracks in ice. And this is just a sort of more sophisticated example of that. So the important point is that if I have some theory of the vacuum and I want to test it, each theory of our vacuum, and which will determine how the vacuum decays, will give you a different picture that then you can measure with this cosmic microwave background, and also the pictures we take of large-scale structure and galaxies. So again, we make our observation today. We had inflation took place. It gave rise to these initial primordial seeds, and as they evolve in time, we get the large-scale structure. And we take a photograph of this, and this is the picture that we have today, looking back at this quantum mechanical effects of the vacuum. So what turns out, I'm showing lots of pretty pictures, but of course there's a lot of mathematics behind this. And when you look at the data and you try to explain it, you find that the simplest explanation really requires higher energies than what we currently understand in the standard model. And in particular, it's very far beyond the standard model. So again, we can ask, how much beyond the standard model is this? Well, the energies have to be at least larger than a factor of 10 trillion. So that's 10 trillion. 10 trillion you're very familiar with. This was 4 days ago, so it's not up to date. But the current national deficit So the current national deficit is around 10 trillion. And the good news is if you're planning on moving to Europe, this is only about 3 euros. Okay, so we need to go beyond the standard model. And to go beyond the standard model, we need to ask, we want a theory. We've seen we need a theory that can explain both gravity and quantum mechanics at the same time. And we only know of one consistent theory that can try to do that, and that's string theory. Of course, people have had a lot of fun at the expense of string theory. So here we have a cartoon representing this fun. So I just had an awesome idea. Suppose all matter and energy is made of tiny vibrating strings. Okay, what would that imply? I don't know. Well, so what I want to do for the rest of the talk is suggest what we might know. So string theory gives a very rich prediction for what the vacuum would look like. We're in search of the vacuum, the quantum gravity vacuum. And this will be manifested in experimental observations, as we've seen with the microwave background and with the evolution of structure. So in this way, inflation really acts like a microscope. It's a microscope looking back into the quantum vacuum and allowing us to see the nature of particles. And if we really do believe in string theory, that means as we take this cosmic expansion backwards to smaller and smaller distances and to hotter and hotter temperatures, the string-like nature of particles should come about, and we should be able to see them. And so that's what this picture is supposed to represent. So what I want to do today is, we've had past talks on string theory that were very fascinating. And what I want to do today is just give you a notion of how this can connect with the cosmological perspective. So there are basically there are crudely three new ingredients that string theory predicts. One is the presence of strings, of course, because it's string theory. The other one is brains, which you can think of as higher dimensional objects that we can either live on or that can be present in the universe today. You can just think of them as this little plane here. That would be a 2-brain. And then the other generic prediction is the existence of new dimensions beyond the 3 plus 1 that we live in today. And so this is an idea of what we might think these new dimensions look like. So what I want to do now is discuss how each one of these could play a role in cosmology. So first of all, we had this nice graph of a phase transition, and we were talking about how the vacuum decays, but we didn't really have a theory of the vacuum. I just sort of said this idea. So what string theory can do is it can provide a possible realization of this idea. So this is something called brain inflation. So the idea is I have 2 brains here that are living in some space-time, and the distance between the brains will be related to how long this inflation is going to last. So then if I allow these brains to evolve in time, they'll attract each other, and they'll go together like this, which corresponds to what we talked about earlier for the phase transition. And then when the brains finally meet and they annihilate with each other, they release this energy, forming the particles that we see today, and this corresponded to the end of inflation. So this is one realization of inflation, and there are many other ones which I won't have time to go through today. So again, this is just one example, and there's many, just inside brain inflation, there's many configurations you can look at, there's many possibilities, there's a landscape of possibilities. But the important point is that each possibility corresponds to a certain set of predictions for these primordial seeds that will then evolve in time. And so in this way, we can observationally test the predictions of string theory. So next, let's look at the case of extra dimensions. So extra dimensions are a generic prediction of string theory. Typically, you can have 10 or 11 extra dimensions, no more than 11, so it's not that you're just making up things. Mathematical precision requires no more than 11. But the point is, as you all know by sitting in this room, we expect these to be very, very small. We live in 3 large dimensions, and we cannot see the other dimensions, or at least have not seen them yet. So you can ask again, how small are the dimensions? So we know that string theory tells us that we should expect this to be about that many times smaller than your thumb. So they're very, very small and very, very difficult to see, but they do have observational predictions. But what I want to focus on today, so I won't be able to say much about their observational predictions today, but these extra dimensions do affect the CMB observations that I was talking about. Unfortunately, I won't have enough time to say something about that today. But what I want to talk about today instead is another problem, and that is the question of, if they're so small, how did they get so small? Or am I just trying to sort of tuck something under the rug and say that there's these extra dimensions? So in 1989, Brandenburger and Vafa suggested an idea, which was basically if I combine all these additional ingredients that are predicted by string theory, these extra dimensions, strings that can wrap around these extra dimensions, so this is a cartoon representing this idea. If I put all these ingredients together, what do I expect? So I have extra dimensions, I have strings that can wrap them, and then I have strings that would not wrap them. And so what they suggested is, first of all, if they noticed that if I have strings wrapping dimensions, this can keep dimensions from expanding. So if I'm in the early universe, everything is very, very small. We saw that number. And I fill the universe with strings, extra dimensions, brains, all possible things, and I allow the system to evolve from this very, very small size, what will happen? And so what they noticed was that the strings, if they're wrapping a dimension, will keep them from expanding. But in 3 spatial dimensions, these strings will be able to find each other, they'll intersect with each other, and they'll annihilate. So they will cease to wrap the dimensions. And so this number 3, unfortunately, this is a very mathematically difficult to explain, so I will not. I will just say that it turns out that 3 seems to be a special number, which is related to the fact that a string is a one-dimensional object. And from this mathematical fact, you can actually explain why 3 dimensions would grow large. So the idea is that the 3 dimensions will grow large, they will be freed by these, but the strings will take all the other dimensions that are present and keep them small. And this explains why we live in 3 space-time dimensions, 3 plus 1 space-time dimensions. So instead of compactifying these dimensions, as the jargon goes, we're actually decompactifying the dimensions that we live in. And everything else stayed at the natural scale, which is the string scale. So what I've just told you is string theory has already made a prediction, and the prediction is that we live in 3 plus 1 space-time dimensions. So is that really a prediction? And so this is not really what we want when we're trying to test a new model or a new theory that we have. Again, observations are beginning to scrutinize these string models with the observations of the CMB. But what I've done, for example, with the 3 plus 1 argument, is we've explained a known known, and that's not really enough. What we need to do is give a unique prediction, and that unique prediction needs to be something that we don't know, or a known unknown, which would even be better if we had an unknown unknown. So for those of you that don't know what I'm referring to, that's it. So what we need from string theory is a unique, one prediction of something that we did not know about, essentially. But it turns out string theory has a very rich structure. The vacuum is very complex, and there's many, many possibilities. And in fact, in this scenario I've talked about where you have strings wrapping dimensions and keeping them fixed, you could have different parts of the universe and different sets of the subsets of dimensions expanding at different times in different places, and it can be a very complicated structure. And so the picture of the universe could end up something like this, where we live in, say, this little blue region here. This is our entire universe. But then it gives rise to baby universes and came from a previous universe, and they're connected by these sort of umbilical cords, which can then stretch and break, or they can remain connected, and you can sort of make any story that you want. The idea is you have so much structure, so much mathematics, and so much possibility that it can lead to an entire landscape of possibilities. And so the question is, where do we live on this landscape, and what do we do with this landscape? So this has been one of the criticisms of string theory. So you can imagine that this is the vast landscape of possibilities, and sort of every valley could correspond to the world we live in. It could correspond to the standard model of particle physics. But on the other hand, other valleys will correspond to other universes that have different properties and different speeds of light and different physics going on. And so it's, again, our job to explain this. And this is just coming along with the complexity. So another question you can ask, if we live in this universe, you can ask who lives in the other universes. So this, again, this is as time goes by. So as time goes by, the idea is these universes can keep giving rise to other universes. And then you can ask yourself, are the properties of our universe just a consequence of our need to be able to make this observation in the first place? That is, if I'm here to ask this question today, I had to live in a universe that evolved in such a way that these small fluctuations were the right magnitude that I showed you, and so they could evolve and give rise to the CMB that I measured and give rise to the structure that I see today. And if this did not happen, I wouldn't be here to ask the question, so it's just sort of a consequence of the fact that I can ask the question, or something like that. So the question is, does this mean the end of science? And some people have suggested that it does. In fact, this has led to many arguments among physicists. But most of the people that work, or don't work, actually, most physicists agree that it's a little too early to ask this question. And the reason is that we're just beginning to understand these subtleties of the vacuum. So I mentioned earlier that the LHC will turn on and test this notion of the vacuum. And this is the low-energy vacuum. It's the standard model. It's the electroweak theory, the theory where the weak force joins with the electric force, the magnetic force, and they are supposed to come together. And we're just beginning to understand where the masses of particles come from and testing this notion. And we have a very well-tested standard model, and we understand all of cosmology before that. And sort of every moment in time, you could have made this argument that the argument that I previously made, that are the particles' masses just what they are because I'm here, and if I didn't have that mass, then I wouldn't be able to ask this question. So we need to be careful when we make such observations. And also, what I hope I'm getting across today is that there are current and future observations that will be vital for connecting string models of cosmology with the cosmic microwave background, allowing us to test the theory. So let me give you a brief summary, since I've said a lot today. So the first thing is that cosmology has become a precision science. There's lots of data and lots of observation. We really understand the picture I had of the early universe expanding and cooling. We very much understand where the primordial elements the atoms come from. We can precisely predict the amount of hydrogen in the universe, and it follows exactly this Big Bang cosmology picture. We've predicted the cosmic microwave background, the idea that as the matter cooled down, that the light should stream away from us and be preserved, and we should see it today. We made that observation. We saw it was smooth, but we got a surprise. There were small fluctuations. That told us how all of the galaxies got here. So that was another surprising and well understood now phenomena. And all we really need is the cause of these initial things. And we saw that inflation provides that. So this is at 10 to the minus 34 seconds after the Big Bang. So we have a remarkable amount of knowledge, and now we just really need to sort of uncover the mysteries of the vacuum. And hopefully experiments like LHC will help us do that. And so, again, we need to have an explanation for this data, and we need to know where these initial seeds came from. And we have seen that inflation did provide an answer. We just need, inflation, the important point is that this idea of inflation is really a way of thinking about how to solve these problems. But again, if we don't have a fundamental theory to tell us where this inflation is coming from, this fundamental theory of the vacuum, then we will not be able to consider this a complete picture. It will just be an idea in search of a theory. And what I hope I've given you some sense of, although I didn't get to say much, was that string theory may be this theory. And it's a little too early to tell, because we're just beginning to see, for example, the brain inflation model I showed you. We're just beginning to be able to construct such models and make predictions that we can then test with observations. So thank you.
Saturday Morning Physics is sponsored by the Physics Department of the University of Michigan, by the Dr. Remlois Tiffany Endowment, and by gifts from friends of the program.